Hello, I'm Wu Xiangyu, a training instructor for the Mechanical Design Group at the THM Regional Branch. Currently, I'm in charge of the computer-aided mechanical design and drafting class using AutoCAD and SolidWorks software. In today's session, we'll introduce the practical use of 3D printer. The applications of 3D printing are extensive, spanning from mechanical and electronical engineering to architecture and even in the food industry. 3D printer allows us to transform our conceptual designs into physical objects quickly, capturing both the shape and structure of our ideas. In the following part, we will begin the practical part of the class. Before operating a 3D printer, let's first discuss what a 3D printer is. Business operation arises due to consumer demand to meet consumer needs. Products must be meeting the following criteria. First, they should have the simplest design without compromising on aesthetics or functionality. Second, the material should be chosen with careful consideration of physical properties, appearance, cost, and processability. Third, the manufacturing process should be economical while meeting precision requirements. The above 3 points are fundamentally about how to provide consumers with affordable products of high quality. The appearance and function must be taken into consideration. It's crucial to process the material in the most economical way, with the simplest design to make the price to be acceptable to customers. Now let's look at the application of 3D printer. As we just mentioned, it began with creative design to the final completion of the product and the following market. Let's look at this slide. When the opportunity arises, in order to turn this opportunity into the next step design, we'll need to design and draw the models through drawing software. After that, we will generate a tangible prototype out of the drawn model, allowing for evaluation of appearance and structure. In the evaluation process, there will be a lot of modification. After modification, we'll proceed to model making, so-called open tooling. After the tryout, we can begin product making and put the product on shelf. The role of 3D printer, as we have seen, is a role of modeler in the process. Through the 3D printer, we can quickly materialize our creativity. Both the appearance and structure of the model can be created by the printer. Using the example of artificial joint development, the initial step involves creating a model in design software. Here we can see on the screen the human bones. With the design file in hand, we proceed to slicing software, orienting and scaling the model as needed, then doing slicing. The finalized file is saved as a readable G-code files ready for 3D printing. Once printed, usually the model contains movable hanging parts, which require supporting parts to be successfully 3D printed. So, after printing, we need to remove the extra supporting parts outside the model. Sometimes additional processing like polishing would be required to get the model we depicted in the software. Then we can thoroughly inspect and test the model's functionality and experience. Now let's further investigate the mechanism of 3D printing. As the name suggests, 3D printing is akin to printing documents, except that it outputs three-dimensional objects. This process, known as additive manufacturing, involves stacking materials layer by layer to create the final product. Next, we will introduce the process of actual 3D printing. As we introduced previously, we need to use CAD to draw the 3D model of our creative design. Then the drawing will be saved as a STL file readable for slicing software. Then the file is analyzed in slicing software. After confirmation, we can finally begin 3D printing. As we mentioned earlier in the printing process, sometimes there are hollow or hanging parts. There will be supporting parts to support them to allow 3D printing to process. After printing, the supporting parts can be easily removed from the final product. The final product can also be refined through various second processing, like for example, drilling or milling. We can see on the screen the condition of the model after printing and before removing the supporting parts. Okay, currently there are two common 3D printing ways. 3D printing products, as we mentioned, are usually highly customized products with small quantity and large variety. This kind of product we have to pay attention requires us to save on the material and processing costs. So there are two common 3D printing methods. One is called fused deposition modeling, FDM. The other is stereolithography, SLA. First, I will introduce the fused deposition modeling. The fused deposition modeling, or FDM, involves extruding heated filament through a nozzle, layering it to build an object. The advantage of FDM is that it supports materials like ABS and PLA. The disadvantage is it can leave visible layer lines. Because of the lines, FDM is considered less delicate, but such a printer is cheaper and easier to operate, so it's an entry-level 3D printing technique. The second method is stereolithography. It uses a layer to harden liquid resin layer by layer. The most common application is called SLA. SLA creates a highly detailed, smooth surface suited for complex, high-precision objects. However, SLA materials are more costly, and the machine requires specific environmental conditions for preserving materials. The cost is higher than FDM, and the optimal operation is more difficult. Our 3D printer uses here features dual extruders and offers high-speed, low-noise printing. The noise it creates as measured on site is only 50 decibels. You can use it in classrooms. The printing and computer drawing can be done at the same time. The 0.4 caliber allows us to print delicate objects perfectly. We can apply various materials including ABS, PC, and TPE. It can also print objects combining both flexible and rigid materials on one model or produce multicolored models. Let's now create a creative model. It contains a moving part combined with another part. We will define it as a rack and cage, like a rack in a bird cage. Okay, we'll use SolidWorks to draw and create a model. First, we open a new file, select Basic Settings. The features, reference, geometry, and the sketch are checked. Okay, here we go. We have an isometric view. Choose an upper plane. Start the sketch drawing. Activate a polygon. Put the center of the circle on the base point. Change the number of sides to 4. Okay, checking the direction as horizontal. Alright. We set the size of the model to be 48 mm. Then we will use the isometric view. Extruded base, mid-plane, the height is 48. Okay, next, we set a cubic. We define the inner diameter of the cage. We choose the upper plane, the uppermost plane of the object as the drawing plane, normal to it. Okay, choose the sketch. Draw the original instruction to sketch a circle. The center on the base point. Next is also a circle. We set the diameter to be 18 mm with an outer contour of 40 mm. Next, we will use these two contours to prepare for cutting. Okay, isometric view. Check the depth of cutting 12. Confirmed. Okay. This is the first cutting we see. Next, we use the contour of extruded cut 1 to process the other 5 planes. Click Sketch 2, check Edit, Copy, then click on the other 5 planes to be cut. Next, the second plane, Ctrl-V Paste, open Sketch 3, positioning, overlapping the sketch to the base point. Confirmed. Cut. Isometric view. The same depth 12. The third plane, Ctrl-V Paste. Open sketch number 4, normal to it. Overlapping the center to the base point. Isometric view on the cutting 12. Confirmed. The fourth plane. Choose it. Ctrl-V. Open sketch 5. Normal to it. Cut. Cut isometric view. Okay, the fifth plane. Choose it, Ctrl-V, Edit, Sketch number 6, normal to it, Center, click on the center of match base point, Confirmed. Cut isometric view, the same depth 12, Confirmed. Okay, the sixth plane, click it, Ctrl-V, Edit, Sketch 7, normal to it, the same. Click on the center to match the base point. Cut. Isometric view. Confirmed. Cutting depth 12. Confirmed. OK. Check the box to answer the system is all done. Alright. On the screen we can see the finished model. Next, we'll draw the finished model. First, save the file. File name, Rack in Cage. Okay, next, as we save the file, we'll save another accessible file for the slicing software to access for 3D printing. The file extension is STL, so we save it as a new file and choose the file extension STL. Keep the file name as wreckingcage.stl, saving the place we set. Confirmed. Yes. Now let's all the moves from drawing to saving readable STL file for 3D printing. We finished drawing the model in the CAD software. After that, we save the model as an STL file. Once the file is saved, we open the slicing software and locate the file we just saved, ensuring it's saved with the STL extension. We then open the file, and the model that appears on the screen is the creative model we just designed in the CAD software. Once the model is in the slicing software, the first step is orientation. Making sure the model's direction is correct. Next, scaling, since 3D printing doesn't necessarily require a 1-to-1 ratio. We select the model, and on the left side we see functions for orientation, scaling, and moving. For now, the screen shows as we have drawn and set in the drawing software, the model size is 48 millimeters. We need to consider whether the model needs to be printed at a 1-to-1 scale, as this will require more time and materials. After consideration, we will scale it down. So we put the cursor to scale. By selecting the scaling command, we adjust the ratio to 45%, reducing the dimensions to 21.6 millimeters on all XYZ axes. After confirming that the real size dimension meet our requirements, we tell the slicing software about the model material. Shown on the screen as a cursor pointing number 2 is PLA, the material for the model. We need to let the system know this model shape will be printed using the 3D model printer filament. We select the model and choose the second output pathway, executing it. We can see the second pathway, list number 2, will output the model filament. On the screen now, you can see the color changes from light yellow to a darker orange. Next, since we are using model material and supporting material, two different types of materials, so the model will require supports for any overhanging parts. Thus, we are opening the option about removing the support parts, particularly the so-called, it's on the right side, so-called wide and prime tower. Located on the right side, click on this icon opens a parameter box where we check to enable the wide and prime tower. Next, we set the size of a tower diameter to 15 millimeters and the minimum volume as the default setting to 25 cubic millimeters. Its position as shown in the gray area on the screen is set to 50 millimeters on the y-axis and 0 on the x-axis. The position should be set not too far from and not overlapping with the model. Next on the screen, the wide and prime tower placement is optimal, not too close and not overlapping. After we confirmed the function of the tower is active, we can close the parameter. Then on the quality of the model, we'll open again the parameter to check if the line width matches the nozzle at 0.4 and the extrusion width is also 0.4. Okay, confirmed again we just is a shell, the part of a wall thickness setting contained in the parameter. We change the default wall coil count from 3 to 5 to strengthen the model. This modification ensures a more durable print, while all other parameters remain at default settings. After completing these settings, we close the pop-up settings similarly. Now we can go to the button in the right corner where there's a slicing function. We perform the slicing action, and once it's done, the system will inform us that the estimated 3D printing time is 1 hour and 26 minutes. The amount of material required will also be displayed on the screen. During the printing process, before actually starting on the 3D printer itself, there's a preview function in the slicing software. We can enable this preview function on the right side and adjust the completion percentage by lowering the slider to the lowest level. We can observe the print on the initial base layer on the platform to the entire printing process. By moving the cursor along the completion percentage, we can gradually check the model and support material to see if there is any abnormalities that need correction. If upon inspection the model and support material are in good shape with no issues, we can return to the preparation screen. The original one, once the slicing file is ready, we save it using a CF card as the external storage device. We then proceed to save a file, click on the CF card as a storage device, then it completes the slicing software file storage tab. Next, we start the machine adjusting the height of the nozzle in relation to the platform, having an overview of it. Use the sensor to detect and measure the platform level. So we install the sensor at the fixed position on nozzle, securing it with a screw with appropriate tightness. This is also plugged with a specific foolproof orientation, so need to worry about inserting it incorrectly. After installation, move to the control panel. The panel says Start Printing, Motor Controlling, and other settings. Once all preliminary settings are done, we select Start Printing. Now here we are. In order to finalize the setup, we first enter the motor control section where there are 4 options. We talked about the sensor. The machine includes a small program which automatically performs point measurements using the sensor. We simply need to initiate this function. The sensor will use predefined levels to detect the platform's flatness. Once the calibration is completed, we remove the sensor. Now the screw is loosened. Unplug it carefully. Detach it from the nozzle. Now we can see that after completing this calibration, we will apply material on this platform. Here is where the material is printed and grown up. This platform is a plane of tempered glass. It's smooth, so we need some glue to make the material adhesive. We use a glue stick to apply on the glass platform, just a thin layer for the function of added adhesion. After applying the glue, we activate the platform's heating function to quickly set the glue, making it congeal. Okay, we complete the glue application. Next, we install the filament from a 3D printer. We can see that the 3D printer supports dual materials. This allows us to use 2 types of materials on the printer. 2 channels will be introduced into the nozzle with 1 channel for material exit. Now we apply the main material for base. We use a PLA filament on a light yellow color. Okay, here's the main spindle. We put it on. Then we install the supporting material on the other spindle. Supporting material is for hanging parts. This dual material printer provides structural supporting for parts of the model that are suspended. The two materials are different, so it's designed to detach easily after printing. We ensure the correct orientation before securing the filament on the left side. Alright, the main filament is put on and supporting filament is on the left. The filament is open just now. The packager bent the end and hooked it onto the holes. Pulling it out, we need to trim the cooked end of filament with a model cutter. Cut it with an angle to create a sharp tip. And then insert it into the first white tube for output. Next, we see the second white tube leads to the filament into the nozzle, which heats up from 0 degree. So here's another operation on the control panel. We set the material's heating temperature to 220 degrees Celsius. Activate heating. The default platform temperature is 24 degrees Celsius, which will also activate heating. The fan also be turned on to confirm its functionality. After activation, we can hear its operation. That means it is working. The screen shows the temperature rising. The default plant temperature is 65 degrees Celsius. Now it's 33. Once it reaches 220 degrees Celsius, the filament will start to melt. Now that the nozzle is at 220 degrees Celsius, we can see it already at a temperature high enough for the filament melting. Now on the right side of the panel, we can see the output direction of filament. The arrow is downward, which means the filament is going down. Now push down while you observe the second duct in the nozzle to check if the excess material is feeding, going down. We can see the nozzle squeeze out extra material. We can use our right hand to feel if the filament is going. It's also necessary to check the nozzle, see if it's feeding smoothly. This way, the filament is conducted successfully. By performing the same procedure, we put in support material. Like the previous one, we trim the cooked end and feeding it through the other white tube, feeding in a certain length. On the panel, this downward arrow on the left means the direction of the supporting material. You can also see the extra filament is disappearing, which means it's going down of the filament. Then check the noose to see if the end is squeezing out properly. Again, use your right hand to feel the smoothness of conducting. If there is resistance during feeding, we can press this spring mechanism on the machine. The gear will slightly release to allow for adjusting the angle of conduction. If it's because the end is not pointed enough, we should trim it again. Then put it in the second tube again. Like the previous part, we send the supporting filament down the second tube. Check the nozzle for extruding condition at the same time. Now look back at the control panel for this downward arrow. Meanwhile, feel with your right hand if the filament is going down. Again, check the nozzle if a supporting filament is going smoothly. If it is, then no problem. Okay, now the filament are installed. Here is something you need to pay attention. Between the first and second tube, here is a little tip. Be sure to leave a bit of slack between the tubes to allow the nozzle to move downward without stretching the filament. If it's too short, the pulling down action might break the filament. Next, we adjust the nozzle to platform height using a sheet of A4 paper to measure the gap. This A4 paper thickness we've measured is 10 lines, which means 0.1 millimeter. Now we insert this paper between the nozzle and the platform, switching to the panel. Among the 4 items, the second from left is called height setting, pressing it. Next, the screen shows the downward distance adjustment options: 10 mm at one move, 1 mm, 0.1 mm, and 0.001 mm. Now, the nozzle and platform are far apart, so we choose 10 mm, alright. So here is a direction option, the positive direction on z-axis and negative direction on z-axis. Now we make it downward, which means negative adding, so now we are moving the nozzle on the negative direction on z-axis. Okay, now is a hint. We will need to reset the height to 0. Here's an icon that looks like a home base. Press it and the machine will reset the height to 0. Next, we move the nozzle down. Okay, 10 mm down once. We gradually move it. Meanwhile, our eyes are set horizontally aligned with the height of the nozzle. Thus, we adjust the height of the eyes so we can see the nozzle. When the nozzle is about 2 to 3 centimeters away from the plane, we need to make a buffering here, so we'll slow it down. Switching the moving distance to a smaller scale is safer. We change from 10 into 1 millimeter, making it go down slower. Again, here we have the record of the original height before measurement for your reference. Currently, it's 16.59. That means the height is about 1.5 centimeter. Okay. Now, in this distance, we go with the speed of 1 millimeter at a time. Here we are. When it's close to 5, now it's 6.49, we need to switch to 0.1 millimeter move, making the move even smaller. This will ensure a nozzle not to hit the plane. Okay, we move from 6.49 down step by step, moving at 0.1 millimeter at a time. Okay, when the height is within 1 millimeter, we will use this A4 paper. We try to draw it out. Alright, now it's not yet touching the plane, so the height of this paper is 10 lines, which is smaller than the height. Now the distance is 0.99, bigger than the thickness. Okay, let's go down. It's a 0.2. We can't use 0.1 anymore. We need to switch to 0.01. This is the smallest unit now. Go. Getting down at 0.01. Now the pressing button needs to be slower because the nozzle could touch the paper anytime now. So how do we know it's reset to 0? It's be done when you can draw the paper but cannot push it away. Now it's okay to draw and push, so we need to go down. Okay, it's a 0, see? We can draw but it arcs when you push. This means the nozzle and plane are very close, reaching the height we set. Now we can draw the paper away, setting the z-axis at 0. The system will ask you if you want to set z-axis at 0. Press yes. Okay, now it's down. Press the home base icon to reset to 0 and the nozzle will go up the high position. We just complete the calibration for height of 3D printer now, which means we set the nozzle and plane with A4 paper. Before we conduct the printing model, we can run a height testing program. This program includes 3 identical test squares measuring 1.5 by 1.5 centimeter with a thickness of 0.4 millimeter, which should match the nozzle layer height. We can observe the 3 pieces to see if they match the thickness of 0.4 millimeter. If they are too thin, the extra material will accumulate. If they are too high, then the height is over 0.1 millimeter. Then the layers will separate. Okay, the first piece is ready. The default program prints 3 pieces because we can check the first piece while the machine is running. We can pick it up. Okay, this piece here, as we said, can be examined by stretching. We mentioned that if the nozzle and the plane are more than 0.4 millimeters apart, the material will not be rightly connected. It will shatter. If the distance is smaller than 0.4, material will accumulate. Now we see the surface smooth, and we cannot tear it apart with gentle pulling. That means the high calibration was successful. The reason why we need 3 pieces is when we have a situation of too high or too low, we can intervene anytime to adjust the height, make it higher or lower. For example, if it's too low, we can take over and elevate the nozzle. If it's too high, we can make it go down. After adjusting, we can check the second piece to see if the height is okay. If it has reached the perfect height. Okay, this is the piece we just printed. We can gently stretch it diagonally, focusing on observing if the lines are connected with the set thickness and the clear edges. If the nozzle is too high, the pieces will fall apart. If too low, the material will overflow the edge, which feels rough in your hand. Now I got this, which is not good. You can easily tear it apart with stretch. This means the nozzle is too high and the lines didn't connect well. Okay, as we have completed adjusting and gradually modifying the height, we could expect ideal results from the thin test printings. This is the final adjusted piece which cannot be split with gentle stretches, not even showing cracks. Also, its edges are also intact. That means the current height is good. Okay, we use the slicing software to analyze the results and save the data to the memory card. On the machine, here is a card slot. We can insert the memory card in. On the control panel, the entry screen says it's ready now. First, we need to locate the file, confirm the file name, press it, and the machine will detect the current temperature of the nozzle. When it has reached the ideal temperature, it will automatically start. At the same time, we need to observe if the filament is extended to proper length, allowing the nozzle to move down to the plane. Now it's waiting. The temperature is 100 degrees Celsius, while the temperature we set to start is 220 degrees Celsius. So the system will heat it up to 220 degrees before beginning to print. By the way, in this operational panel, apart from displaying the current reading of nozzle temperature, we can also see the required manufacturing time for the workpiece we are about to create. There is a clock symbol here which shows the completion percentage. Okay, the temperature is also displaying on the screen. Currently, it's 194 degree. We need to heat it up to 220. This 220 degrees Celsius melting temperature for our model material PLA. Okay, when the model is completed, the machine will give a beep as a notification to us that the printing is finished. Now we take a spatula to create a large inclined angle facing upward at the base of model. We gently push with our hand. Sometimes we may need to change to another angle, preventing the model from detaching too forcefully. We can also remove it from a third direction. Once we see that the model is detached smoothly, we can gently lift it with our hand. Next, we proceed with removal of supporting parts from the model just completed on the 3D printer. During the process, as we are using tools that are designed to peel, there may be sharp and pointing parts, so it's essential to wear protective gloves. For safety, we use needle nose pliers, model pliers, and smaller straight needle nose pliers, and as well as finer tip model pliers. We'll use a large sharp tip cutter box and various trimming tools. After putting on gloves, we will use long thin needle nose pliers to grasp and remove the easily detachable parts, applying a little bit of appropriate force to do it. At first, there's more contact area, so we remove the support from multiple directions. After removing the excess support, we have got a round shape. The original conceptual model we drew with the picture. Because the image does not give us an actual object to discuss and check, now we have completed this model. With 3D printer, we can assess the appearance and the actual movement of the object within the frame to see if any size adjustments are needed. If there's any discussion or adjustment required, we can go back to the picture, edit it, and print it, and edit and print again. So we finally reach a conclusion. We can begin with the conclusion to proceed on-site processing. Based on the actual processing and our model, we carry out discussions. Since it's only for discussion purpose, we can reduce the scale to save materials and shorten production time. After confirming the complicated parts like appearance and functionality through these discussions, we can confidently process with machine. This way, we avoid the hassle of needing further modification after the object has been made.